Previously, we saw that as we increased the magnitude of charge 1 while we maintained charge 2's magnitude constantly, that increased the magnitude of the force between charges 1 and 2. When we plotted our values against one another, we got a straight line from which we deduced that the force between the two charges is directly proportional to charge 1's value. But what about charge 2's value? So in this investigation, we're going to do something very similar, but this time we're going to keep charge 1 at a constant value of 50 times 10 to the power minus 6 coulombs, and we are going to vary charge 2's value. What do you think that we're going to find? Will we find the same kind of effect as we found before, or will it be different now because it's charge 2 that's being varied? First of all, what's the question we're asking? How does charge 2, Q2, affect the force between two charges? Or to be more exact, how does the magnitude of charge 2 affect the magnitude of the force between the two charges? What are we going to keep controlled between the treatments? This time, charge 1's value must be kept constant. And again, we must keep the distance between the two charges constant. I'm going to keep the magnitude of charge 1 at 50 times 10 to the power minus 6 coulombs. And again, I'm going to keep the distance between the two charges 4 meters. So we need a table into which we can put our data. Complete this before you continue. Table showing the relationship between charge 2 and the force between the two charges. Q2 is measured in coulombs. Force between the two charges measured in newtons. So we open our simulation. Charge 1's value is set at 50 times 10 to the power minus 6 coulombs. We start off with magnitude of charge 2 at 200 times 10 to the power minus 6 coulombs. We find that the force between the two is 6,1 newtons. Notice that's the magnitude of the force. The direction happens in this case to be attraction because we've got a positively charged and a negatively charged particle. Oppositely charged particles always attract one another. Had they rather been like charged, either both positively or both negatively charged, that would have changed the direction of the force to be repulsion, but would not have changed the magnitude. It would still have been 6,1 newtons. Now we increase the magnitude of charge 2 to 300 times 10 to the power minus 6 coulombs. The force also increases to 9,2 newtons. Q2, 400 times 10 to the power minus 6 coulombs, force 12,2 newtons. Q2, 500 times 10 to the power minus 6 coulombs, force 15,3 newtons. 600 times 10 to the power minus 6 coulombs, 18,3 newtons. We put all of that into our table. What do we notice? As we increase Q2's value, what happens to the value of the force? Does it get more or does it get less? It gets more. The more, the more. Now the issue is it the more by the same factor? Is this direct proportion? How can we check? The quickest way to check is if we do have direct proportion, then one variable divided by the other will give us a constant value. Let's check if that's so. We find out the electric field strength from Q1 onto Q2 by dividing each force value by Q2's value. 6.1 divided by 200 times 10 to the power minus 6 equals. Do this for all the values, pause until you've done this, and we find 3,1 times 10 to the power 4 in each case. We have a constant. What does that tell us? That tells us that these two are indeed directly proportional to one another. This constant has particular value because it means the electric field strength exerted by Q1 onto Q2. Remember, Q1's value is controlled in this case, and that's why we get the same value. Because this is the force that Q2 experiences for every coulomb of Q2's charge. Electric field strength is force per charge. Electric field strength is measured in newtons per coulomb. Because force is measured in newtons, charge is measured in coulombs, so force divided by charge is newtons per coulomb. We plot the graph, and indeed we get a straight line. If we would extend that line all the way to 0, we would see that indeed it would cut the origin. The straight line through the origin shows us that indeed these variables are directly proportional to one another. You need to complete the labels here and then continue with the movie. Graph showing the effect of charge 2 on the force between the charges. Or to be more exact, graph showing the effect of the magnitude of charge 2 on the magnitude of the force between the two charges. Charge Q2, measured in coulombs, is our independent variable. It goes on the x-axis. The force between the charges, measured in newtons, is our dependent variable. It goes on our y-axis. We We can get the gradient of this graph, rise over run, which is delta F over delta Q2, our highest minus our lowest F value for this data, 18,3 minus 6,1 gives 12,2 newtons. Our highest minus our lowest value for the Coulomb values of Q2, 600 times 10 to the power minus 6 minus 200 times 10 to the power minus 6 gives 400 times 10 to the power minus 6 coulombs. 12,2 newtons per 400 times 10 to the power minus 6 coulombs is equal to 3,1 times 10 to the power 4 newtons per coulomb, which is the electric field strength that Q2 experiences from the controlled Q1 value. So again, the gradient of the graph gives us the electric field strength. What is our conclusion? How does charge 2's magnitude affect the magnitude of the force between the two charges? Again, we can give it in this format. The force between the two charges is directly proportional to the magnitude of charge 2. So we've seen that charge 1 affects the force in direct proportion and charge 2 affects the force in direct proportion. In the next investigation, we bring these two facts together.